Welcome to CECS 228. We're going to continue with basic structures part 2, which deals with functions. And so what that means is that we're going to be taking a look at special subsets of the Cartesian product of two sets, one of which can be relations, or if we place some additional restrictions, that is when we get to talk about functions. And functions are extremely important in mathematics because they are used to model the behavior of nearly anything that can be described as a relationship between two or more types of quantities, from amount accrued in a bank to the trajectory of a rocket in different mediums. In computer science, we use functions to help us analyze the efficiency of algorithms. And of course, we also have the traditional code functions, which very closely resemble a mathematical function. So we're going to be taking a look at these topics. If you're following along with your textbook, you might want to read sections 2.1 and 2.3, as well as 3.2 of Rosen's Discrete Mathematics 8th edition. So on to the first definition, which has to do with relation. So a relation R from the set A to the set B is a subset of the Cartesian product A cross B. And a relation from a set A onto itself is called a relation on A. And for whatever reason, these periods did not print on my notes, so I'll go ahead and include them there. Now the set R, for instance, that contains the ordered pairs A with 0, A with 2, B with 0, B with 2, so on and so forth. This is a relation from the set A to the set B. So if you notice, the first number, the first coordinate of each pair is taken from the set A, and the second coordinate is taken from the set B. So because we have a few pairs from the complete Cartesian product A cross B, R is considered to be a relation. Here's another example, example 1. We're going to be defining two different relations from the set A, which contains Frank, Alfred, Margarita, men, to the set B, which contains the letters A, B, C, D. And just to be careful and differentiate between this B and the set B, I'll go ahead and include maybe like the single quote to say these are characters A, B through F, except for E. Okay, and so one possible relation, again, remember, it's just a subset of the cross product. So the cross product would have all possible combinations between elements in A and elements in B, where the first element comes from A and the second element comes from B. So if I want to, I could, for instance, just take a couple of ordered pairs, maybe like Frank paired with A, and maybe like Frank paired with B, and well, let's do just one more, and maybe like Margarita paired with A, and that is a relation from the set A to the set B because it is a subset of A cross B. So I'll label that R1. Let's create another relation. In this next one, we could have, I don't know, let's say men with A. We'll have Alfred with C, and let's say Margarita with, I don't know, we'll say D. So again, because this is a subset of A cross B, then it's considered to be a relation. So notice in the first relation that we created, we have two different ordered pairs that incorporate Frank into them. So we have Frank paired with A, Frank paired with B. That's going to be the main difference between a relation and a function, which is what we're going to take a look at next. Okay, so a function, we're going to start with two sets, non-empty, A and B. So function f from a to b is a relation satisfying the property that there is exactly one element of b assigned to each element in a. So that is, if f is a function from a to b, and this is the notation that is usually adopted. So if it's a function from a to b, then for an element a in a and two elements b1 and b2 in b, we say that f maps a to both b1 and b2 only if b1 equals b2. So the way that would be expressed using simply logical symbols would be if f of a equals b1 and f of a equals b2, then that means that b1 and b2 are the same. Another way to read that, we like to think about A as the set of input elements. So these are the elements that are put into the function, and B is the set of output elements. So if we input an element A and it gives us an output B, but it also gives us an output B2, then that means that B1 and B2 are the same output. Okay, that is the definition of function. And so, for instance, if we take a look at example number 2, it's a little bit hard to read, but we have a diagram representing the function. In this case, we have Adams, Chow, Goodfriend, Rodriguez, and Stevens getting mapped to the letters A, B, C, D, F. So they're asking us if it represents a function. So the inputs would be the names and the outputs would be the letters. That means that for every input, we have to make sure that it gets assigned to exactly one element in the set of outputs B. Okay, so this is A and this is B. If we take a look at atoms, it gets maps to A and only to A, so that looks good. If we take a look at Chow, Chow is getting mapped to C and only to C, so that looks good too. If we take a look at Goodfriend, gets only mapped to B, Rodriguez only gets mapped to A, and Stevens only gets mapped to F. So that means that since we have, I'll just draw a dot, dot, dot here. Since every element of A gets mapped to exactly one element in B, then this function is, this relation is a function. Okay, let's take a look at part B. So part B, we have a function from the set of real numbers to the set of real numbers that is defined by f of x is equal to 1 over x squared. Now again, so what that means is that we're trying to determine whether every input number gets mapped to exactly one output. Okay? That is in B. Okay, so in this case, A is the reals, B is the reals. Well, in this case, it would be true that almost every real number gets mapped only to one output, except for 0, right? What happens if we plug in 0? Well, f of 0 would mean we have 1 over 0 squared, which is 1 over 0, which is undefined. And undefined is not part of the real, the set of real numbers. So since undefined is not a real number, then f is not a function. because again, we require that there is exactly one element in B that is assigned to each element in A. So in this case, we found one element in A, that meaning the 0, such that there is no element in B that gets assigned to it. Okay, so that would not be a function. Okay, here's example 3. Give an example of a relation that is not a function. Well, we've already seen one up here. Okay, this would be one possibility. Another one would be maybe something like f of x is equal to plus or minus square root of x. Okay, because in this case, every input gets assigned 2 output values. Another, so this is one example. Another example could be, for instance, if I have the set A with elements, let's just say 1, 2, 3, and B with the set of elements, let's say A, B, C. And if I if I define a relation, f of 1 is A, f of 2 is B, and f of 1 is C. Let's do f of 3 as well. F of 3 is, let's say, A. Well, in this case, this rule that we've applied here, that 1 gets mapped to A, but 1 also gets mapped to C, would break the definition of function. So this would not be a function because of this definition. So that's something that's worthy of noting. A relation will be a function if basically no ordered pair has the same, no two ordered pairs, I should say, has the same first input, value, but two different second coordinates. So a relation is a function if there are no two ordered pairs with same first coordinate but different second coordinate. Okay, well now we're going to introduce some more terminology that will allow us to create more structure using functions. Those definitions are for domain, codomain, image, preimage, and range. So if f is a function from A to B, we say that A is the domain of the function f, and B is the codomain of the function f. If f of A is equal to B, then we say that B is the image of A, and A is the preimage of B. And finally, the range of f is the set of all images of elements of A. So let's take a look at example number 4 to better illustrate what these definitions mean. What are the domain, codomain, and range of the function that assigns grades to students in example 2a? So if you take a look at 2a, and this was the function that it's referring to. And if we're looking at domain, domain would be the set of all inputs. And those were the students' names. So that would be Adams, Chow, Good Friend, Rodriguez, and Stevens. Okay, so we have our domain. Now, codomain, remember, is the set of all possible outputs. So all possible letter grades would be A, B, C, D, F. And finally, the range. Well, what is the range? The range is a set of all images of elements in A. So that means that it's the set of all elements that actually get mapped to from a set, from an element in A. So if you take a look at the outputs, all of the letter grades except for D have a corresponding input. So that means that the range only includes A, B, C, and F. Okay, take a look at example number 5. Let f be the function that assigns the last 2 bits of a bit string of length 2 or greater to that string. So for instance, if you have f with the input bit string 11010, the output of that would be the last 2 bits 10. What are the domain, codomain, and range of f? Okay, so let's start off with what is the domain. The domain is a set of all possible bit strings. So they tell us that it takes that, or it assigns the last 2 bits of a bit string length 2. So basically any bit string length 2 or greater would be a possible input. So I'm going to write this using set builder. I'm going to say x such that x is a bit string. And the length of x is greater than or equal to 2. All right, now what is the codomain? Okay, well, the codomain would be bit strings length 2, right? And bit strings length 2, we can actually list what they all are. They would be like 1, 1, 1, 0, 0, 1, and 0, 0. That would be all possible outputs for that function. And then what is the range? Okay, well, here we have to think about what elements of the codomain are going to have a corresponding input. Well, what is a possible input? The input are all possible bit strings, and they all have to get mapped, right? In a function, every single element in the domain has to get mapped to an element in the codomain. So because we're considering all bit strings length 2 or greater, we know that we're going to come across bit strings that have that end in 1, 1, 1, 0, 0, 1, or 0, 0. Right? So that means that the range and the codomain are actually the same for this problem. I'll just write a little note here. Also notice the range and codomain are the same because the domain or I'll say because every element of the domain has to be mapped. and the domain contains all possible bit strings, length 2 or greater. So we are bound to find bit strings that end in these digits, in those bits. Okay, example number 6. Let f be a function from the set of integers to the set of integers, and let it assign the square of an integer to this integer. So that basically means we have f of x is equal to x squared. What are the domain, codomain, and range of this function? So again, well, the domain, they tell us what it is. The domain is simply the set of all integers. And the codomain, they also tell us what it is. It's the set of all integers. Now, what is actually mapped, or what actually corresponds to an input in the codomain? Well, if f of x is equal to x squared, that means that we're not going to have any negative integers as part of the range, right? And on top of that, we're only going to have perfect squares as part of the range. So for instance, 0, 1, 4, 9, so on and so forth. And so I'm going to write this as set builder. I'm going to say the range is the set of elements that are natural numbers. So natural numbers, remember, it's integers 0, 1 through greater, but that satisfy the condition that they are x squared. That x is equal to, well, okay, let me use a different variable here because I don't want it to get confused with that x. So it's a set of all elements y that are natural numbers such that y is equal to x squared, where x is some integer. If you wanted to list them out using roster method instead, you could also do that. So you could also say it's 0, 1, 4, 9, 16, so on and so forth. Perfect squares. Right, that brings us to image of a set. So let f be a function from the set A to the set B, and let S be a subset of A. Then the image of a set S, which is denoted f of S, is the subset of B consisting of all of the images of elements in S. So what that means is that f of capital S is the set of all images f of S, such that S is in the subset S. So I think this is probably better understood through a visual. Okay, so let's say that this is set A, and this is set B, and we have a subset of set A called S. Okay. Then whatever these elements get mapped to, their images, they're going to be somewhere in, they're going to form a subset of B, which we call f of capital S. So whatever these elements are, these images, they form this subset f of capital S. Okay, so for instance, let A be the set of elements A, B, C, D, E, and B be the set of elements 1, 2, 3, 4, where f of A is equal to 2, f of B is equal to 1, f of C is equal to 4, and f of D is equal to 1. Oh, actually, one more, and f of E is equal to 1. What is the image of the subset S is equal to B, C, D? And actually, before I continue, let me just correct something I have up here. So just so that the diagram is consistent, if S, the subset, has 4 elements, then it's going to map to 4 images. And so I think I had one extra. All right. Okay, so we're trying to find what is f of capital S, where S consists of these elements, B, C, and D. So that is going to consist of images f of B, f of C, and f of D. And if we take a look at what is f of B, f of B is 1. What is f of C? That's 4. And what is f of D? That is also 1. So that means that we have 1 and 4. Okay. Now some operations on functions that we can define are addition, multiplication, and composition. So the addition of two functions, and in this case we're assuming that f and g are both functions from set A to set B. So if we have the sum of two functions, f plus g, then that's simply defined as f of x plus g of x. If we have the product of two functions, f times g, and notice they do write of x, so you'll see it in this notation. What that means is f of x times g of x. And finally, if we redefine g so that it's a function from A to B, and f so that it's a function from B to C, the composition f of g of x is defined to be f with g of x as an input. And so the order of this actually matters. G of x that is going to output something into B, right? And then f is going to take that element from B, whatever this is, and is going to map it to C. So in order for a composition to work, we always have to make sure that the output of the inner function is the domain of the outer function. Okay, so I'll write that. So notice, in order for composition to work, the codomain of the inner function which in this case is g of x, we'll just write IE instead, must agree with the domain of the outer function. So let's take a look at some examples. Example 8. Let f of 1 and f of 2 be functions from the set of real numbers to the set of real numbers, such that f1 of x is equal to x squared, and f2 of x is equal to x minus x squared. What is the sum of the functions, and what is the product of the functions? Okay, so f1 plus f2, and to be consistent with the notation that we saw in the definition, I'll just say of x. That is defined to be f1 of x plus f2 of x. f1 is x squared. f2 is x minus x squared. And then if we simplify, we can combine the like terms, x squared minus x squared. So that'll simply give us x. And so finally we can simply write f1 plus f2 of x is equal to x. Okay, the second function they want us to find is the product, f1 times f2 of x. And again, that simply means it's f1 times f2 of x, which means we're multiplying x squared times x minus x squared. and that is going to simplify to x cubed minus x to the fourth, because we do distribute the x squared to form that product. And so we're going to get f1 times f2 of x is equal to x cubed minus x to the fourth. All right, example number 9. Let g be the function from the set ABC to itself, such that g of A equals B, g of B equals C, and g of C equals A. Then f is the function from the set ABC to the set 1, 2, 3, such that f of A equals 3, f of B equals 2, and f of C equals 1. What is the composition of f and g, and what is the composition of g and f? So the composition of f and g, that means that we're doing f of g of x. That's the first one. That means that g of x is going to be the input of function f. And so how would that work? Well, that means that we have to consider all of the possible inputs of g first, and then apply f to those to the outputs that correspond to those inputs. So here's what I mean by that. G is defined for A, and it gets mapped to B. So that means that f of g of A is equal to f of B, which is equal to 2. So ultimately then, when you have the composition f of g of A, that is going to be mapped to 2. So let me just write that. F of g of A is equal to 2. All right, now that was only one element. We have to consider all the possible inputs for G, which are B and C. So let's look at the next one. G of B is C, so that means that f of g of B is going to be f of, well, let's see, g of B is C, is going to be f of C. Now, f of C is 1, so that means that f of g of B is mapping to 1. Okay, next one, we have one more, g of C. G of C is A, and that means that f of g of C is going to be f of A, which is going to be 3. Our final result is f of g evaluated at C is going to be 3. Okay, so these three together make up the composition f of g of x. Notice this worked because the output of g of x, the codomain of g of x was ABC, and the domain of f is ABC. So that's why it worked. Okay, so I'll write it down here. The codomain of G is equal to ABC, which is the same as the domain for F. That's why that worked. Let's try taking the composition of G with F. So we're looking now at G of F of X. So that means G is the outer function, F is the inner function. Now, before we continue, let's look at the codomain of F, because now we want to make sure that the output of F is part of the domain of G. So the codomain of F is the set 1, 2, 3. And the domain of G is the set of elements A, B, C. Okay, so they are not equal. So technically we're not going to be able to perform this composition, but even if we didn't check for this condition, we'll see at the moment that we try to take the composition at the first element. So if I try to take an element from the domain of F, which is ABC, I would do something like, okay, well, F evaluated at A is 3. And now if I try to take G of F of A, that means that I would have G of 3, but G of 3 is not defined because G is only defined from ABC to itself. Okay, this is undefined. So therefore, this is not possible. And the first indication that this was not going to be possible was through this check. Okay, let's take a look at example 7. Let f and g be functions from the set of integers to the set of integers, which are defined by f of x is equal to 2x plus 3, and g of x is 3x plus 2. What is the composition of f and g, and what is the composition of g and f? So again, just to write out the notation that we've seen before, the domain of f is the set of integers, and the codomain is the same thing. Same for g, it's from z to z. So when we check whether we can compute f of g of x, what we would want to check is that the codomain of G agrees with the domain of F, and in this case it does work out. But just to write it out, the codomain of G is a set of integers which is equal to the domain of F. Okay, so that checks out, which means we can proceed. Okay, so that means we have F of G of X, and I am replacing g of x with the 3x plus 2 into f as an input. So that means that everywhere we have an x for f of x, which is here at the 2x plus 3, I'm going to be replacing with a 3x plus 2. Okay, so let me just make a note of that. Everywhere you have an x, you're going to replace it with the input. In this case, my input is this 3x plus 2, so I'll have a 2 times 3x plus 2, and then I'll have plus 3 from the original f definition. Okay, but here I'm simply replacing x with this input. And so if we simplify, what we're going to get is, distribute the 2, we get a 6x plus 4 plus a 3, so that's ultimately a 6x plus a 7. And what about g of f of x? Well, in this case, since now the outer function is g, we have to make sure that the codomain of f is the same as the domain of g, which it is. But just so that we get accustomed to always checking that, I'm going to write it down. The codomain of f is a set of integers, which agrees with the domain of g. So now we're going to replace f with the 2x plus 3. And this is our new input for g of x. So everywhere you have an x, you replace it with a 2x plus 3. That's a 3 times 2x plus 3 plus 2. And now if we distribute to 3, we're going to get a 6x plus 9 plus 2. So ultimately that becomes 11. The next definition that we're going to consider for functions is that of injective. And this is part of the discussion on injections, surjections, bijections, and invertibility. So what does it mean for a function to be injective? Again, we're going to pretend the domain is represented by A and the codomain is represented by B. We say that F is injective, also called one-to-one, if and only if for any two elements that are part of the domain, f of A1 equal to f of A2 implies that A1 equals A2. So what that means is that there will be no two distinct pre-images with the same image. Alright, so basically if you take a look at the range, nothing in the range is going to correspond to two different inputs. So for example 11, determine whether the function f from the set a, b, c, d to the set 1, 2, 3, 4, 5 with this definition is injective, meaning if it's one-to-one. So when you have the elements listed out this way, one quick method that you can check for to see if it's injective is to list out the domain versus the range. Or I guess in this case we'll list out the whole codomain. Okay, so have possible input A, B, C, D, and codomain 1, 2, 3, 4, 5. A gets mapped to 4, B gets mapped to 5, C gets mapped to 1, and D gets mapped to 3. So if nothing in the codomain, no element in the codomain corresponds to more than one input, meaning there's no two arrows pointing to the same element in the codomain, then that means that it's injective, because it means that we only have one input corresponding to it. So in this case, this is injective because no image has more than one pre-image. And so you can think of image, again, this is output. No output has more than one input, corresponding input. Here's another example of something that is, actually this is the drawing for example 11 on top as well. I just decided to draw it one more time. So notice, a function is going to be injective if there are no two ordered pairs such that they have the same second coordinate but different first coordinate. And so just be careful because this is actually very similar to the definition of function, right? In the definition of function, we said a relation is a function if there are no two ordered pairs with the same first coordinate but different second coordinates. So that means there is no one input that gets mapped to two different outputs. In injective or one-to-one, what that means is that, or the difference is that the second coordinate, meaning the output, there's no one output that has two different inputs that correspond to it, meaning it doesn't have two different first coordinates, no two ordered pairs with different first coordinate but same second coordinate. Right, for example 12, they're asking us to determine whether the following functions are injective. Part A is the set of the function from the set of integers to the set of integers, which is defined by f of x is equal to x squared. Okay, well, if we take a look at, let's say, f of 2, right? F of 2 is 2 squared, which is 4. But if we take a look at f of negative 2 squared is also going to be 4. So what that means is that if I list out the elements, the ordered pairs that are part of the function f, I'm going to see ordered pair 2 with 4 and ordered pair negative 2 with 4. So what that means is that I have two ordered pairs with the same second coordinate but different first coordinate. So this is not injective. Not injective. Because we found at least one output with two different corresponding inputs, or one image with two different pre-images. We could also, I mean, this is one of infinitely many, right? If you take 9, 9 has corresponding pre-images, -3 and 3. If you take 16, you're going to have -4 and 4. So basically, all of the elements of the range have two pre-images. And I should say except 0, right? 0 is the only one that has one pre-image, which is itself 0. So every element in the range, i.e. every image except 0, has two pre-images. That's why that is not injective. What about part B? So in B we have a function g from the set of reals to the set of reals, which is defined by g of x is equal to x plus 1. Okay, so for this one, we might suspect, hey, every number that I input, any real number that I write, the output is one more than the real number that was input. So I'm not ever going to find any image, any real number that is going to correspond to two different numbers if it was the result of adding 1 to those two numbers. So the way that we can prove it is we can assume that there is, so we're going to prove it by contradiction. We're going to assume that there is one image with two distinct pre-images and then see what comes out of that claim. And so assume that there exists two input values, I'll call them x1 and x2, that are real numbers, such that x1 and x2 are not equal to each other, so they are distinct, and g of x1 is equal to g of x2. I mean, they have the same output, i.e., they have the same image. Okay, then what does that mean? Well, then that means that x1 plus 1 is equal to x2 plus 2, plus 1, just by the definition of g, right? G of x is x plus 1, so that means replace x with x1 and replace x with x2 on the right-hand side, and both of those expressions are going to give you the same thing. Well, if that equality holds, then I should be able to subtract a 1 from both sides, and what that's going to result in is in the expression x1 is equal to x2. But that contradicts our initial statement that x1 cannot equal x2, so therefore we've encountered a contradiction. And what that means is that there are no such numbers x1 or such real numbers x1 and x2 such that x1 does not equal x2 and this is true. So i.e. what that means that if for every element, so for any elements x1 and x2 that are real numbers, if g of x1 equals g of x2, then x1 will equal x2. And that is the definition of injective. Now, two definitions, or I should say more like four definitions that are related to this idea of injective are those of increasing and decreasing. So if we consider a function f from the real numbers to the real numbers, we say that f is increasing if for any two real numbers x and y, if x is less than y, then f of x is less than or equal to f of y. We call it strictly increasing if instead of having less than or equal to, we have strictly less than. F, on the other hand, is decreasing if for any input numbers, x and y, if x is less than y, then f of x is going to be greater than or equal to fy. And then we say strictly increasing if this is a strict inequality rather than a greater than or equal to. So what does that look like? Well, let's go ahead and just draw a diagram or a decreasing function. A decreasing function might look something like this. That continues. That continues somewhere, as somewhere as x goes out to infinity. So why do we say that this is decreasing? Well, pick any two numbers. I'm going to call this maybe like x, and I'll call this y, and that's to be differentiated from the x and y axis. Okay, so these are just two random numbers. We prefer to call them x1, x2. That also works. I'm only using x and y because that's what we have in the definition on page 7. Okay, but in this case, we can say that this x is less than y, right? So in this case, x is less than y. And what can we say about f of x? Well, f of x is going to correspond to this point. Okay, f of y, I'll use red here to denote the y. Okay, f of y is going to be actually very, very close. Okay, might even agree. I mean, at this point where it's completely flat. There might be some, if x were a little bit closer, f of x and f of y would be the same, but it's a little bit less than f of y. So as you can see, it doesn't matter where I pick the two numbers. Like if I pick f of x more to the right, it would mean that f of x will still be greater than f of y. And if I get it closer to y, then at this point that they're exactly the same thing. But as long as I choose x being less than y, it is going to be true that f of x will be greater than or equal to f of y. So that's what it means to have a decreasing function. Now, if you have a strictly decreasing function, that means that there are no flat areas in your function. Right? So maybe it looks like this, where it doesn't matter where you pick your x as long as you pick it somewhere before y. F of x, so in this case, this is our f of x, is going to be greater than f of y. So that is called strictly decreasing. And let me just be complete here. In this case, x is less than y, and you have f of x being greater than f of y. Okay, what if it's increasing function? Well, increasing function, the diagram will just look exactly what it sounds like it's increasing, where maybe there are some parts that are flat before it continues to increase. So for instance, if I now take x at that point and y at this point, f of x is going to be here. F of y is now going to be larger. So we say that a function is increasing if regardless of where we pick x, as long as x is less than y, you get the property that f of x will be less than f of y. Be less than or equal to. And again, the area that would represent the equal to would mean if I pick like x somewhere here maybe, and y very close to it, it looks like at that point that the shape of the graph might be a bit flat, so they're going to have the same output value. And strictly increasing just means that there will be no flat areas. It'll just be constantly increasing. So if you pick an x here and a y value here, oops, so that you have the same property, x is less than y, then you're going to get an f of x value that is always strictly less than the f of y value. Right, so when you have one of these two situations, a strictly decreasing function or a strictly increasing function, what's going to be true is that the function will be injective. And those are the two remarks that are found lower on page 8. We're actually going to write the proof to part 1. So we are going to do it by contradiction. We're going to start by assuming that f from A to B, so we'll say that the domain is A and the codomain is B, is a strictly increasing function. But it is not injective. And now what does that mean? Well, it means if it's not injective, that means that we have an element in the range. We have an image or an output that corresponds to two different pre-images or two different inputs. So then there has to exist some element, which I'll call y, in B, such that, actually, and then let me also say, and there exist two elements, let's call them x1 and x2, in A, such that f of x1 is equal to y, and also f of x2 is equal to y. Okay, so one input, two outputs that correspond to it. So such that this is true and x1 does not equal x2. So two distinct inputs that correspond to the same output. Alright, so without loss of generality, let's say that x1 is the one that is smaller, is the smaller of these two elements. Okay, so suppose, without loss of generality, that x1 is less than x2. Well, if x1 is less than x2 and f is a strictly increasing function, that means that we are in a situation where this is like x1 and this is like x2. That means that f of x1 has to be less than f of x2. So in such a case, f of x1 is strictly greater than, is strictly less than f of x2. Now that's a contradiction because we said that f of x1 is equal to y and is equal to f of x2, meaning they're the same output, right? But here we're saying that their values are actually different. Their output values are actually different. So this is a contradiction. Okay, so hence, if f is strictly increasing, it must be injective.